It's my pleasure this evening to introduce Dr. Marcello Descanzi, who is an associate professor of mathematics at Vanderbilt University. He earned his PhD in mathematics from the State University of New York at Stony Brook in 2012, same year I got my PhD, very nice. He works on mathematical aspects of general relativity and fluid dynamics, with a special focus on how gravity and fluids interact with one another. So, you know, cakewalk, right? I'm back, okay. Marcello and his collaborators solved an 80-year-old problem in mathematics and physics with the discovery of the BD and K theory. And that reconciles the Navier-Stokes equations of fluid dynamics with Einstein's equations of general relativity. I will get through these announcements. Oh, I just got one more here. Okay. That is why we have 3 backup microphones. I will get through these. Can everybody hear me all right? All right, good. All right, so Marcello is the recipient of a 2018 Sloan Research Fellowship, a 2019 Dean's Faculty Fellowship, and a 2023 Chancellor's Faculty Fellowship. His research is supported by the National Science Foundation and the Department of Energy. He's also the author of more than 50 scientific articles, the upcoming book, Relativistic Viscous Fluids, and the book, Who Me? I'm a Mathematician. Some of you may have seen this book. This is my favorite of the things that I just listed off there. But he is the star of this book, and we also have copies of the book in our lobby tonight, and they are available for a donation of any size. Okay, and better yet, you can even get it autographed this evening. I don't know how much he's charging for autographs, but if he charges too much, I'll autograph it for you. I don't care. So, and then one other little note, Dr. Descanzi let me know tonight that he's available to come to schools for free to speak to classes, to talk about the book that he's in, to talk about subjects like this. Pretty much anything. So if you want to know more about that, you can Google him and put in Vanderbilt, and he's going to instantly. Okay. So without further ado, and before this mic goes out, join me in welcoming Dr. Descanzi for this evening.
Is this mic on? Yep. Perfect. Okay. I want to thank William for the invitation, the introduction, and the audience for being here. So I'm going to just start saying, as William described, I want to emphasize I am not an astronomer. I am a mathematician. So I will tell you about black holes, general relativity, but also a little bit about their underlying mathematics. So what you see here in this picture is the first picture of a black hole taken by the Event Horizon Telescope in 2019. So let's recall that a black hole is an object whose gravity is so strong that not even light can escape from it. And later I'm going to explain how that works in more detail. Now, the image you see here is not of the black hole itself. It couldn't be, because light does not escape a black hole, but rather is a picture of the gases surrounding the black hole. So, to start, what I want to do, I will show you 2 videos illustrating the behavior of black holes. I'm going to show the videos to you, and I'm going to describe the videos as they are playing. Now, don't worry too much if you don't understand everything I'm going to be saying while the videos are playing, because during the presentation I'm going to come back and explain every part of what I'm saying. But I think it's nice to show the videos just to motivate everything. So here we see an illustration of 2 black holes orbiting each other. You don't see them directly because, well, they are black. Light cannot escape. So all you see are these black regions in space from where light cannot escape, but that's where the black holes are located. But what happens is that the pull, the gravitational pull of a black hole is so strong that even the light of distant stars that pass near the black hole is distorted, and that's why you see this kind of blurred region here. So that's when the light of distant stars passes near a black hole, is distorted. And we are going to get to the details of how that works later. Now, you have two black holes here, so they also attract each other. So eventually, they merge into a single black hole. That's what you're seeing here. Let's run the video once more because it's really nice. And I should emphasize that this is not an actual video of black holes. This is computer generated using a computer, right? But it's based on the actual equations that describe a black hole. So there they go again, they orbit, and boom, they merge into a single black hole. Now, in 2016, the LIGO collaboration measured effects of a merger of two black holes. And the story is as follows. Here again is an illustration of two black holes orbiting each other. The strong gravity of black holes creates gravitational waves. I'm going to explain what these waves are, but in a nutshell, they are ripples in space that propagate by expanding and contracting space itself. So let me go back here. They are like these ripples here that you can see. So maybe you can play again. Imagine these black holes are orbiting. As they move, they create these ripples in space, which are caused by space itself expanding and contracting. Okay, so then you can see here this bright light is depicting these ripples in space. And very much like waves on the surface of the ocean move by bending the surface of the water, these gravitational waves move by bending, by curving space itself. And we are going to get to how that really works. Now, when these black holes merge, when they collide, they produce gravitational waves with a tremendous amount of energy. So these gravitational waves expand through space, and eventually they reach Earth. Now, because gravitational waves move by bending, expanding and contracting space, when they pass through Earth, they expand and contract the entire planet. That's what they do. However, this effect is very small. Yeah, that's what should happen. But this effect, let me go back, is in fact very small. And it has been exaggerated here in the video. The Earth is not really doing that, right? So this is an exaggeration, but that's in reality what is happening. And to measure this effect, we need a very special instrument, that's LIGO. So here's a picture from air from LIGO. Okay? And the way that LIGO works is as follows. Okay, so we're going to take a view of LIGO. A laser beam is sent through a partially reflecting mirror that splits the beam into two. These beams are reflected back, and at the center there's a mirror that sends them to a detector. Okay, so here is again an illustration of this process in slow motion. Now, what happens is that when a gravitational wave passes through the detector, it expands one of these arms in one direction and contract the other arm in the other direction. So this is illustrated here in the picture. Because it expands one arm in one direction and contracts in the other, what happens is that when these laser beams are reflected back, there's a shift between them. There's a shift between the peaks and the valleys of these laser beams. And this changes a pattern that's eventually detected by the detector here. That's what LIGO measures, is the shift in these two lasers coming from expansion of the arms in one direction and contraction of the arms in the other direction. Now, all this sounds stuff of science fiction, right? Black holes trap light, space itself bends, expands, and contracts, and gravity is causing all this. So to understand how this is really happening, we have to talk a little bit about the theory of relativity that goes back to Albert Einstein. Now, the theory of relativity relies on some mathematics that was developed by the mathematician Bernhard Riemann in the 19th century. Okay? So what we're going to do now, we're going to take a little detour to talk about mathematics, okay? And I hope that's not going to be too painful. But then we're going to go back and talk about black holes and general relativity, all the funny stuff, okay? So the key concept that we need to understand the theory of relativity is that of the curvature of space. And to explain that, let's start with a very simple picture. Let's imagine a two-dimensional plane, okay? Like the flat screen that's projecting this slide, just a two-dimensional plane. Now, if I take 2 points here on the plane, this point and this point, and I want to join them by the shortest distance between these 2 points, that's just a straight line. Okay? That's going to be the shortest distance between these 2 points on the plane. And there are other properties that are intrinsic to the two-dimensional plane. For example, if I draw a triangle here where the angle between these two sides is 90 degrees, then necessarily the other two angles have to be less than 90 degrees. That's because the sum of all angles of a triangle on the plane has to be equal to 180 degrees. Okay, but now let's consider a two-dimensional sphere. In other words, think of the surface of Earth. Think of the surface of the Earth. And I want you to think only of the surface, not of Earth's interior, nor the space above it, just the surface. Now, if you consider only the surface, there is also a two-dimensional object, like the plane that we had in the previous example. But the surface of the Earth has very different properties than a plane. So let's see why that's the case. So if you want to move from the North Pole to a point here in the equator through the shortest trajectory, through the shortest path, what you do, you just start at the North Pole and walk straight. Right? Start at the North Pole, walk straight. You don't turn left, you don't turn right. But now, from your point of view, you are walking straight. But in reality, you are walking through this meridian along Earth. Okay? You're not walking on a straight line from the point of view of the surface of the Earth. You cannot even draw a straight line on the surface of the Earth. So what this is telling you is that the shortest path, the shortest trajectory between 2 points on a sphere, between 2 points on the surface of the Earth, it is not a straight line, but is an arc, like this meridian. Okay? So that's very different than what happened in the plane. Now the shortest distance is given by this curved arc. And there are other properties that are very different on the surface of the Earth. So if you draw a triangle here by taking these two meridians from the North Pole and connecting them through the equator, you are going to get a triangle where these two angles is 90 degrees each. This angle is 90 degrees and this angle is 90 degrees. Therefore, the sum of the angles of a triangle on the surface of the Earth, which means on a sphere, is more than 180 degrees, because it's going to be 90 plus 90, which is 180, plus whatever this third angle is. So it's more than 180. We therefore see that the way that lines, triangles, angles, etc. behave on the sphere is very different than how they behave on the plane, on the flat plane that we saw before. In other words, the geometry of a sphere is different than the geometry of a plane. Okay, so that's the important message. The geometry of a sphere is different than the geometry of a plane. Now, if you think about, this is not very surprising because the Earth is not flat. When I was preparing this presentation and looking for pictures, I went to the website of the Flat Earth Society. But I was very disappointed that they didn't have a good picture. So this is a picture from space.com. Okay. So yeah, we know that the Earth is not flat, right? But here's the important thing. You might think that this behavior of the fact that lines and triangles, etc., behave on the surface of the Earth in a way that's very different than the plane, that's okay. That's caused by the fact that the Earth is curved, right? The surface of the Earth has curvature, it can bend. And you might think that's okay because the Earth, the surface of the Earth, is a two-dimensional object lying within a three-dimensional space. That's why it can bend, because it has room to bend along the third dimension. However, what I want to explain next is that it is possible to talk about curvature without imagining a larger space where you sit inside. Okay? We can talk about the curvature of a two-dimensional object without ever considering that two-dimensional object sitting inside three-dimensional space. And once we understand that, then we can start understanding how the very space that we live in is curved. And that's going to bring us back to the theory of relativity. So here, I want you to imagine that this rubber ball represents the surface of the Earth, and these hexagons are like curved paths, curved trajectories along the surface. And what we can do, we can take a flashlight and project these hexagons onto the flat table, onto the plane. And if you do this very carefully, you're going to get a distorted but otherwise faithful representation of the surface of the Earth onto the plane, where the shadows are going to be representing these hexagons. Okay, you can do this very careful. And you get a representation of the surface of Earth on the plane. And you can do this experiment at home just to see how these things change with the flashlight. So here is a schematic representation of what I just showed you. These yellow beams, they represent the flashlight, the light rays, and they are projecting the surface of the Earth onto the plane. So for example, this triangle here is projected onto this shadow here. Okay? Now, if you think about, that's precisely what we do when we draw a map of the globe, right? You're just projecting the surface of Earth with its continents, oceans, and so on, onto a flat piece of paper. Now, if you look at this, for example, you have this curve, this red curve, which is the shortest distance between the South Pole now and this point on the equator, is projected onto this purple curve. Incidentally, this is why if you look at the trajectory of an airplane on a map, or like when you look on the flat screen on your airplane, you're going to see the trajectory is not a straight line in general. It's going to be something curved. Now, what is happening is that the airplane is trying to take the shortest trajectory on the surface of the Earth, which is going to be some curve like this red one, right? Which, when it's projected on the map, on the flat surface, is going to be curved like this purple curve here. So that's why you're going to see some trajectory like this. Okay. So I was on a plane once, and I was looking at the map, and there was this guy sitting next to me, and he was very upset that we were not taking like the shortest distance. We were making all this curve, right? And I tried to explain to him that that's what was happening, but he wouldn't take it, you know. Okay. So now I want you to forget about the surface of the Earth and think only of the shadows here downstairs. Okay. In other words, let's forget about the surface of the Earth, but let's continue to look at these projections. Okay, let's continue to look at these projections. So now we're going to focus only on the shadows. So even if you forget where these shadows came from, they are a faithful representation of the geometry of the sphere. Okay, so that's the important message. You have these shadows, now you forget that they're coming from this projection that you did the flashlight, but the curves that you have here are still a faithful representation of how curves and triangles, etc., behave on the sphere. These shadows, this projection, is still a faithful representation of the geometry of the sphere, but now you are seeing this on the plane, on this two-dimensional plane downstairs here in the picture. And now here comes the crucial thing. We are going to create a new geometry on the plane. And we're going to create a new geometry on the plane by declaring, by definition, that lines on the plane obey the same rules as the shadows obtained by projecting from the sphere. In other words, I'm going to declare that the geometry that I have on this plane now is going to be such that the shortest distance between points is given by an arc like this. The triangles in this new geometry that I'm going to create are allowed to have angles that add more than 180 degrees, and so on. Now, when I do that, because these rules that I'm declaring, they are a faithful representation of the geometry of the sphere, and because the geometry of the sphere is curved, because the sphere has curvature, it means that this new geometry that I'm creating here also has curvature. But the key point that I can talk about these lines and angles, etc., on this plane without ever thinking about a third dimension. I do not need to imagine that this plane lives inside a larger space. And that's how you can talk about a space being curved without ever thinking that it lies inside a larger space. Okay. Now, I know that you have questions, right? Can we really do that? Can we just make up rules that say that the shortest distance between points is not a straight line on a two-dimensional plane? Can we just make up rules like that? And the answer that I'm going to explain in the next slide is yes, we can actually make up rules and create new geometries. So, I want you to think about the rules of mathematics as rules of a game. Okay? Why is a touchdown worth 6 points? Well, it is worth 6 points because the people who created the game decided so. But they could have as well created football where a touchdown is worth 4 points or 8 points and so on. Okay, so we could have different types of football games. And some of you are going to recognize this picture here, right? So that was the majestic victory over Alabama. Okay. So we can actually create games with any rules we want. We can just make up games, right? There are only two requirements when you create a new game. First, our rules have to be self-consistent. A touchdown cannot be worth 6 points and 8 points at the same time. I have to pick one. I'm free to create a game where a touchdown is worth 6, 8, 10 points, but I have to pick one. Cannot be both at the same time. Okay, my rules have to be self-consistent. And the second requirement is that I cannot change the rules mid-game. Once I decide what my rules are, I have to stick to them. Okay, so those are the two. And other than that, I can create games with any rules that I want. And the magic is that the same is true to mathematics. Okay, I can create a geometry on the plane, which is the standard geometry we learn in school, where the shortest distance between 2 points is a straight line, where the angles of a triangle add to 180, and so on. But I can also create the rules of my geometry where the shortest distance between 2 points is an arc like this, where triangles have angles adding to more than 180 degrees and so on. But I have to pick one, right? I have to be self-consistent. I cannot say that the shortest distance is going to be a straight line and an arc at the same time. I have to pick one. Now, let me make something absolutely clear. I'm not saying that you can just make up that 1 plus 1 is equal to 3. Okay, that's not what I'm saying. Okay, I don't want anybody like, oh, the math professor at Vanderbilt said that I can just make up my rules. No. But why? Well, because when you calculate 1 plus 1, you are employing the rules of arithmetic, right? And the rules of arithmetic have already been set to you. Okay, people decided thousands of years ago, like going back to the Greeks, what the rules of arithmetic are. And when you go to school and you are tested, you are being tested not on the rules that you created yourself, you are being tested on the rules of arithmetic. Okay, and that's why 1 plus 1 has to be equal to 2 and not 3. Of course, you can create a different numerical system where the rules are different. Okay, and mathematicians have actually done things like that. But that's not going to be arithmetic. That's going to be another different numerical system. Okay? Now, everything that I told you about the geometries in 2 dimensions applies equally as well to 3 dimensions. Okay? I can create new geometries in 3 dimensions where lines behave in a different way, where these geometries in 3 dimensions have curvature. And because I can create these things, I can create, in fact, infinitely many geometries. Okay, I can create infinitely many geometries the same way I can create infinitely many types of football, as long as I follow those 2 rules. I'm self-consistent, and once I pick my rules, I stick to them. Okay, so I want to pause for a second to contemplate this idea. We can create new mathematics with any rules we want, as long as we are self-consistent and as long once we set down the rules, we follow them. This means that there is almost no limit to what we can create with mathematics. And that's why I say that mathematics is the freest of sciences. Unlike empirical sciences like physics, chemistry, biology, where you are bound by the rules of nature, in mathematics you can just create new things. In physics, for example, you can invent new theories, but if your theory does not describe nature, you have to throw it away. That's not physics. Now in mathematics, we are limited only by self-consistent and our own imagination. Okay? And that's the beauty of mathematics. And that's one of the most deep ideas in science that I think sometimes is not emphasized, the freedom that we have in mathematics. Okay. But now, if you're not a mathematician, if you're an astronomer, you don't care about all these infinite different geometries, right? You want to know what is the geometry of the space we actually live in. In other words, what is the geometry of our universe? And answering that question brings us back to physics. Einstein's fundamental discovery, which is the foundation of the theory of relativity, is that massive objects with very large mass, they deform, in other words, they curve the space around them. And gravity is a manifestation of the curvature of space. So here is an illustration. Imagine space is like a bed sheet. And if you lay a heavy object down on a bed sheet, it will deform it, it will curve it, like in this picture here. And that's exactly what massive objects do to the space around them. They deform, they curve the space around them. And this explains gravity as follows. So imagine here Earth orbiting the Sun. Because the Sun is very massive, it deforms, it curves the space around it. Okay? And then when Earth is moving, what Earth is really doing is simply moving by inertia. Okay? There is no magical force connecting, attracting the Earth to the Sun. All the Earth is doing is moving by inertia, which means that the Earth is moving through a trajectory that is always the shortest trajectory between any 2 points along its path. But because the space is curved due to the presence of the Sun, the shortest path for Earth to follow is precisely the path, is precisely the trajectory that gives Earth orbiting around the Sun. And that's the origin of gravity. Okay? That's how gravity works. This was summarized very well by the late physicist John Wheeler, who said that space-time tells matter how to move. Matter tells space-time how to curve. So the fundamental lesson of the theory of relativity is the following. The space we live in is curved. Its curvature is caused by objects with mass. This curvature of space is the source of gravity. Okay? That was Einstein's big discovery. And we can now understand why black holes are black. Okay? So remember, black holes are objects where gravity is so strong that not even light can escape from them. But we just saw that gravity is a manifestation of the curvature that an object causes on the space around it. So another way of saying what a black hole is an object that curves space so much that the trajectory that lights follow never leaves the black hole. Okay, let's see how that works. So here's an illustration. We have, for example, the Sun, which is a very massive object, so it deforms the space around it. A much more massive type of star is called a neutron star, so it deforms space around it even more. But a black hole is the king of deforming space, is the king of curvature. It deforms space, it curves space more than any other object that we know. Okay, much more like illustrated in this picture. Now, when light travels through the cosmos, it always travels on a trajectory that is the shortest distance between any 2 points. So if you have a light ray passing here, the Sun, what is happening is that because the Sun is very massive, it's curving space around it, so the light ray is going to follow a trajectory which is the shortest trajectory in this curved space. So the light ray is not going to follow a straight line, it's going to follow some curve like this. Okay? So the light ray is going to pass near the Sun and it's going to feel a bump, but it's going to still pass, go around, and keep going. Okay? Now in a black hole is different. the curvature of space caused by a black hole is so large that if you have a light ray starting inside the black hole, the kind of shortest trajectory for light to follow is one that never leaves the black hole. Okay, so all that the light is doing is to follow again the shortest trajectory, but because of the way that the curvature happens due to a black hole, this shorter trajectory never leaves the black hole. So that's why light never escapes a black hole. And this gives rise to a very interesting phenomena called gravitational lensing, which works as follows. Imagine you have here a very massive object, okay? Could be the sun, could be some other star, and you have a source of light, could be another star, behind it. Now a light ray is going to travel here, but because this object is curving space, the light ray is going to travel across this curved trajectory, and eventually it's going to reach us here. But all we see is the light that comes to us. So what is very interesting is that if we take this light that reaches us, and if we were to trace it backward through a straight line, we would trace it backward and we would reach a point here. So, we would think that the light came from this point, where in reality came from this point. Okay? So if you just traced back in a straight line, you would think that's coming from here, but in reality came from here, but the light ray curved around the sun. That means that when you look at objects in the sky, in general, they're not really where they appear to be. That's how we see them, but they are really their actual position in the sky is different, because the light that's coming is passing through this curved space and bending around stars and black holes and so on. Okay? So now we can go back to this video and try to understand better what's happening. Okay? So here we have these black holes. They are curving space so much that light cannot escape from them. Cannot escape it because, again, light is just following what is in that curved space, the shortest trajectory. But the black holes are not curving only the space inside them. They are also curving the space on its surroundings. So what is happening is that the light of distant stars, it passes near the black hole and comes through an oblique trajectory, comes through a curved trajectory. And that's what causes this blurred region around the black holes. But there is more. All the pictures that I've shown you so far of curvature were static pictures. But in reality, these black holes are moving. That means that when they move, they are curving, they are deforming the space surrounding them in a way that's changing over time. So the way that curvature is changing in the vicinity of these black holes is changing over time. And that's why you see this dynamic phenomena here. Here's another illustration of gravitational lensing. Okay? So when light rays pass near a black hole, they follow this curved path, as we saw, by this lensing. And when a lot of them pass, they focus passing the black hole. By the way, because of this focusing, that's why we call it gravitational lensing. And when they reach us on Earth, that's the kind of picture we see. Okay? And that explains the picture of a black hole captured by the Event Horizon Telescope that I showed you at the beginning. But something even more interesting happens. There are some light rays that in fact go around and make a half orbit around the black hole before reaching us. They come and make a half orbit. And then finally they reach us here, and that's how we would see them. But wait, there are in fact some light rays that go a full orbit around the black hole, and only then they come around and reach us here in this field of vision. Okay? So when you look at these light rays that are making half orbits or full orbits around the black hole, what you would see is this very thin ring of light around the black hole. Okay, those are these special orbits that make a half orbit or a full orbit around the black hole before reaching us. I should mention that this is a computer-generated picture, so this ring, this very thin ring, has not been observed yet. Okay, it's predicted by the equations, but people have not observed them yet. But there is a proposal to launch a space mission called the Black Hole Explorer to actually measure this thin ring around black holes. Okay. Now, this story that gravity, the source of gravity is curvature, also explains gravitational waves. Okay, so we can think of gravitational waves as waves of curvature. Again, all the previous pictures I showed you of curvature were static, but in reality these black holes are moving. So when they move, they are changing the curvature of space around them, contracting and expanding space in a dynamic fashion. So these things are changing over time. And the way that this space contracts and expands and then moves away from the black holes creates these gravitational waves, which are very much like the waves on the surface of the ocean. Okay? And these are the waves that we measure with LIGO. Those are the waves detected by LIGO. And again, this is an exaggeration, right? This effect is very tiny. Okay? But that's what is happening. Okay. Okay. So I talked about Einstein's and Riemann's contributions, and certainly they were key figures in the development of the theory of relativity and modern geometry. But I don't want to give the impression that they did it all alone. Okay? Science is a collective enterprise, and we are always relying on fundamental contributions of other people. So there were many other people that were very important for the development of the theory of relativity and modern geometry. Some of them are presented here. In particular, I want to highlight the work of the mathematician Choquet-Bruhat. Okay? So here are Einstein's equations. These are the fundamental equations of the theory of relativity. I'm not going to try to explain what all these symbols mean, and actually it's not very important right now. I just want to point out that these are very complicated equations. And Einstein himself could not solve these equations in full generality. The first person to fully solve Einstein's equations was Choquet-Bruhat in 1952. She did that on her thesis. The story is that she wanted to do that for her thesis in mathematics. Her advisor told her not to do so because that problem was too hard. She went ahead and do it anyway. We're glad she did. So the message that don't always listen to your professors. So, yeah. So I guess we can say that if Einstein was the father of relativity, Choquet-Bruhat was definitely the mother. Okay, so now I want to tell you about the following. Let's imagine what we would see if we had a black hole right here in front of us. In fact, we don't have to imagine. So this is my colleague, Alex Lupsaska. He's one of the world's leading specialists in black holes, and he created an app called Black Hole Vision that lets us visualize how things behave in the presence of a black hole. So this app is available to download for free at the Apple Store, and is also an open source code available on GitHub, so it can be ported to other devices as well. So what I want to do, I want to give a demonstration of how this app works. Okay, so I'm going to get my phone, bring the app, and let's see, I should mirror and you should be seeing my phone. Okay, so here's like the camera. Okay, so this is the app, so this is our camera, nothing special. Hello, hello. But now let's put a black hole in the center. Okay, and that's what you'd see. That effect that I told you about the light rays orbiting the black hole and distorting the image, that's what you would see. And there are some controls here. So this is called the realistic field of vision because it's really how the black hole would look from the point of view of the camera, because the camera has like a limited opening, right? But if you were to imagine a full opening of the camera, that would look like that. And you also have a selfie mode. So let's do the selfie. You can do like that. Let's see. There is one here. Up, oh, let's up. That's pretty cool, right? But this black hole is in fact a static black hole, right? Or just sitting there. And black holes in nature don't work like that. In fact, black holes in nature, they are rotating. So here there's another setting that lets you take the black hole and change the value of its spin, how it's rotating. And then you can see that again the picture changes. And you can do regular mode or selfie mode, okay? So again, you can download for free this app and just play with it. It's pretty cool. And what is important that this is not make-believe. This is not like a filter for your camera. This is based on the actual equations that describe a black hole. That's how things would really look. So that's why it's not just another filter. Okay, this is based on how things would actually look on a black hole. Okay, so let me stop mirroring this and go back to the slides. Okay. Maybe, I don't know, you can keep the lights on, I'm almost done. Okay, I want to finish with a disclaimer, okay? Here I try my best to convey the essential ideas of relativity and modern geometry, but in doing so, I had to make some simplifications, change some conventions, okay? So I had, to be honest, to lie a little bit to you, okay? But I hope that I was able to maintain the essential concepts intact, that I was able to do this simplification without dumbing things down, because I wanted to really get to the essential concepts of modern geometry and relativity theory. Now, this is a simplification that I did, not because I don't want to explain or because I don't think that people can understand. I did this just for the sake of time, because I had to condense all this in less than an hour. I'm fully confident that all of you would be able to understand relativity and modern geometry given enough time. So if you are interested about this, don't be discouraged, okay? These things are not as hard as they look at first sight, okay? Life is hard. Math and physics are not. And on that note, I want to thank you for your attention.
All right, thank you, Dr. Descanzi. So, anybody have any questions? No questions after all that, right? All right. So we're coming around with some microphones so that everybody can hear, and also we're live streaming this evening so folks at home can hear as well. So yeah, we got a question.
Why are some of the things circling around the black hole not being absorbed into it, such as your face, for example? But the lights that orbit around it and come back.
Yeah, that's a very good question. So there's a threshold called the event horizon of the black hole, which is the region where the curvature is such that light rays, once they enter that region, they cannot escape. Okay, the right analogy is like, imagine you are launching a rocket from the surface of the Earth. Okay, there's a certain threshold beyond which you can escape the surface of the Earth, and below which you cannot escape the surface of the Earth. Okay, the difference is in a black hole, the threshold is such that once inside, you can never escape. But that does not mean that something outside the threshold cannot pass by, be almost captured, but still escape. Okay, there is this threshold that once you're there, you are trapped. But you can come close, almost get captured, but still escape. Does that answer your question?
Thank you. That was really interesting. I'm very curious about how, where you talked about the sort of like not having a, like, sorry, I should frame this better. So where light is getting curved, so where you think an object is not where it actually is because of the apparent position.
Yeah.
How does that work for like trying to figure out where things are located? Because you have so many different gravitational poles, or like where, if you don't, do you understand the curvature and then use that to determine? How does that work?
Okay, that's a very good question. And here I have to remind you that I'm not an astronomer, okay? So, but it's a hard question. People like William spend a lot of time actually figuring these things out, right? I can tell a little bit about one case where that was done, which was in 1919, which was the first experiment that people did to test Einstein's theory of relativity. And the way that they did is the following. If this is the sun, you cannot really see this object because this is very faint compared to the light of the sun. But then what happens is that in 1919 there was a solar eclipse, okay? And then there was a solar eclipse, so the light of the sun was blocked here, so people could see the light of distant stars like coming from this point. Okay, so it looks like it comes from this point. But then half a year later, Earth goes around, and the stars are so distant that this part here is almost like not moving. So you can imagine this part here is not moving. So with the solar eclipse, you saw the star here. When Earth comes around, then now you don't have the sunlight blocking, then you can see that the star is really here. And again, that half year makes almost no difference because the stars are so far away that from our point of view, they're basically not moving. Okay, that's one way you can figure these things out. But how you do that for other situations, more complicated situations, I'll let William respond that to you later. Okay, again, I'm not an astronomer.
No, I was curious about it from the mathematics of it. Is like,
oh, the mathematics is fine. Okay, we can calculate everything or almost everything. What we cannot calculate, you can plug in a computer to calculate. Okay, but how you see how you pick up the data, because the data is very messy. It has noise, it has error bars, right? And that's really complicated. The mathematics we calculate, but how you actually compare the data, that's a completely different business.
Dr. Descanzi, that was fantastic. Thank you for that, watching the math kind of behind the scenes. My question is about the app, right? So when we're looking at the focus versus the object, and so my understanding is we're looking at the black hole in between what we're looking at, right?
Exactly.
So how does it matter how close, like for example, if the black hole is farther towards the kind of position that we're looking at versus is closer to us, how does that kind of affect it when you're looking at that way?
Of course. The app is set up in a way that this is kind of in a preset distance, right? Maybe there's going to be another version that's going to also let you play with other parameters of your problem, but this is, let's just imagine, like a preset distance, right? Does that answer your question?
Sure.
Okay. And if you go to, I guess, hackernews.com, there is a long discussion of the app with all the details of how that works, if you want to read about it.
There was one question online as well. So if light is going towards a black hole and it goes into the black hole and cannot escape, and we have light constantly doing that, would the inside of a black hole essentially be infinitely bright with all those photons?
Well, yeah, okay.
Just a simple yes or no, please.
Okay. The truth is that we actually have no clue of what is happening inside the black hole. Okay, so there is no yes. I cannot give a yes or no answer. Of course, we have theories, we have speculations, but of course, the problem is that physics, in the end, we need data, we need to do experiments, and we cannot get. I mean, we can go inside the black hole to do an experiment, but you cannot come back and tell other people what you saw, right? So that's not very fun, right? But that's the kind of question that, you know, if somebody one day figures out what is inside of black hole, that's a Nobel Prize. That's the kind of questions we're talking about.
I understand matter is not evenly distributed in the universe. How much does that complicate mathematical models?
Okay. You want the short answer or the long answer? Okay. So the short answer is that typically we think that we can imagine that matter is more or less evenly distributed, right? We actually model cosmology as if the matter was a fluid. Instead of being a point particle here, a planet, a galaxy, we imagine this is like a continuum, right? And this continuum is more like an average over all the different, you know, planets and suns and galaxies and so on, okay? But that's an approximation, okay? And it's a hard mathematical problem to actually prove mathematically that that approximation is valid. Physicists, they assume that it's valid because, you know, that is corroborated by the experiments and measurements that they make. But to actually prove mathematically that that approximation is valid, it's a very hard problem, it's an open problem. I think I have a... So sorry, just because, does that answer your question? Okay.
Thank you so very much. It was really, really educational, entertaining, not dumbing down, but definitely simplifying. A question from a 10-year-old: where's the closest black hole to Earth? And to add to that, so we saw in the simulator that the black holes can merge. Is it possible for them to split and separate?
Oh, okay. To your first question, I'm going to again mention that I'm not an astronomer. So, William, where is the closest black hole to Earth?
It was just on the screen up there from your phone.
Okay.
I want to say that is it Cygnus X1? Anybody in here happen to know? Yeah, well, that's 27,000 light years away, so I forget how far. We'll look that up while you're...
Okay, according to my wife, it is the closest known black hole to Earth is Gaia B81, which is located in the constellation of Ophiuchus.
Oh.
Ophiuchus. But that's the internet, okay? Don't always trust what you see on the internet.
Well, don't always trust me either.
Yeah,
so.
don't always, okay? Now, to your second question, okay, so that's a very interesting question because if you look at Einstein's equations, they are what we call reversible, which means that it's completely consistent with Einstein equations that every process that happens in one time direction can happen in the other. So it's completely consistent with the theory that black holes could merge and could separate. But it seems we don't see that happening, okay? So the question is that there is a discrepancy between what the equations tell us that is possible and what actually observe in the universe. Just to give you another example, there are some solutions to Einstein equations called a white hole. A white hole is something that instead of things falling in the black hole and being trapped there forever, things are just spelled out of the black hole, okay? And that's completely consistent with Einstein's equations, but we don't see those things in nature, okay? And it's almost a philosophical question why we have equations that give such a good description of nature, but there are certain behaviors that we do not see in nature that in principle are allowed by the equations, okay? So that's sort of an answer, but not a complete answer. Does that satisfy you? Okay.
Thank you so much, Dr. Discondi, for the talk. It was really enjoyable.
Thank you.
Informative. So one question is, we usually do things at this scale using Newtonian mechanics, and it was very interesting. You said the Earth is just moving under inertia. So is it possible at all to get rid of all forces and even use those concepts on the Earth too?
Yes, so that's a very good question. So let me just step back and give you a little background, okay? So Einstein's theory is the best description we have of gravitational phenomena. But you probably learn, in high school about Newton's laws, right? That tells that there is a force between the sun and Earth. We know, and the force, it depends on the mass of the Earth, the mass of the sun, and the distance between them. And that's like going back 400 years to Isaac Newton. Now, so what happens is that there are certain phenomena, like, for example, this gravitational lensing that was confirmed, that was verified with this kind of experiments using the solar eclipse, that cannot be accounted for Newtonian mechanics. So Einstein's theory of gravity is a more complete theory than Newton's theory. However, for a lot of phenomena, the effects of curvature are so small that we can neglect them. So for example, when you launch a satellite to space, we do not use general relativity. We also we use the old-fashioned 400-year-old Newtonian mechanics. Okay, this is more or less like I told that if you want to walk on the surface of the Earth, the shortest path is going to be an arc, right? Not a straight line. But if I'm just interested in the shortest distance between these 2 points here in this room, the Earth, the curvature of the Earth is so small, right? That's basically flat. So I can imagine for all practical purpose that inside this room, the Earth is flat. It's not, but I can imagine it is, okay? So, and that's a very common theme in science. A lot of times, we have a more complete theory that accounts for more complicated phenomena, but for the kind of things you are studying, you can disregard certain effects and use a simpler theory, even if it's not a correct theory. Okay, does that answer your question?
Yeah, there was.
Okay.
So is there some other story behind even electromagnetic forces and other forces? Do they also have some other effect? Yeah,
okay. So that's a very interesting question. So there was an entire project in the 70s that some people call the geometrization of physics, okay, where people discovered that other forces like the Young-Mills force, right, and the forces, Young-Mills force are the force that corresponds to the electric and strong force, okay? So they're the forces that are responsible for keeping the cohesion of the proton, the neutron, and they're also responsible for something called the beta decay. And the equations that describe these forces can actually be put in a form that is geometric, that can also be interpreted as curvature. But it's not curvature of space. It's curvature of a more abstract object called a fiber bundle, okay? And that's a whole story, but there is this idea that you can actually geometrize all the forces of physics, okay? Now, the difference is that in the case of gravity, you are talking about curvature of the space that you actually live in. For these other forces, we are talking about curvature of these objects called fiber bundles, which are more abstract constructions. So you can ask yourself, okay, so is there a real advantage of thinking in terms of curvature for these abstract objects? Okay, so that's a bit of a long answer, but it's a complicated question.
Thank you.
So Dr. Descanzi is going to be around for a little while, so if you have any other questions...
Maybe there's one last here. She was waiting, I think.
Oh, yeah, I'm sorry. I didn't see it. Yes. Let's do one more here.
Gravity is often described as the bed sheet, a flat surface. But we don't live in a flat surface.
Yeah.
So how do we describe gravity as far as in space when it's not flat, even though there's depression in it, but we are moving around and everything's moving around and everything's moving? That's always perplexed me.
No, yeah, okay, so that's a good question. So the thing is that we do these illustrations because we can only visualize the bending of a two-dimensional surface. We cannot really visualize with our visual apparatus what would be the three-dimensional space itself curving. So that's why we make this analogy that space is like the bed sheet, which is two-dimensional and is curving, right, when you put an object.
So in other words, it's like an infinite number of bed sheets, all stacked on top of each other in other ways
Yeah,
and everything else.
I think that
and they all move.
I think that any type of you can try to think like that, but any type of visualization that you try, I think is not going to be very precise. Okay, because that's a limitation of our visual apparatus. But we know that these things are perfectly well-defined mathematical objects. I was explaining, you can define these geometries, you can describe them with equations, and that's the part where, in physics, sometimes your visual apparatus or your sensorial apparatus starts to fail, but the equation is still there, and they do a good job describing the physics. So I don't know if that's a good answer, but that's okay.
There's one more I want to ask.
Okay.
This is actually from an online viewer. So is a marble going around like the inside of a funnel as it's rolling around? Is that similar to how light would move around the black hole?
Yeah, that's kind of that's similar to her question. That's kind of the picture we draw to try to make this analogy, right? But again, we are always trying to make the analogy where the object is curved, is sitting inside three-dimensional space. So like the funnel would be like this two-dimensional tube, right? Because the two-dimensional tube, you can actually see its curvature, right? And that is, again, an analogy, some way to visualize, but the actual picture is like the curvature is happening in the full three-dimensional space, but we cannot visualize this, right? So that's why our visualizations are always depicting a two-dimensional object that sits inside three dimensions. And that's why I wanted to explain to you that it's possible to talk about curvature without an extra dimension. Okay, because people are always drawing these pictures and causing the impression that you need an extra dimension to talk about curvature. You don't need. Okay, the equations do a good job of describing, just we cannot visualize it.
Gotcha. Well, let's thank Dr. Descanzi for an incredible talk this evening. And if you have additional questions, he'll be hanging around for a little bit. We do have, we've got Jupiter in the telescope. We will hopefully.
Clouds have moved in, so it's iffy.
Okay, so we.
Saturn is still there, but you have to wait for little gaps to come by.
Okay, so we're still on Saturn. So if you didn't get a chance to see Saturn before the talk this evening, you might have a chance if you want to wait for the clouds to move out of the way for a moment. So Dr. Bob will be up at the telescope. We also have a volunteer back here, Mr. Chuck Schlimm. He has brought a smaller version of his typical setup that he brings to our telescope nights, and he can answer any and every question you have about space vehicles of any sort. So I highly encourage you all to go back there and pay him a visit. I want to thank everybody for coming this evening. And again, follow us on Eventbrite. Marsh will be here before we know it, but you never know. We might have a new event pop up on our calendar, and we'd love to see you back up here. So hope everybody has a safe drive home this evening. Bundle up. It's getting a little bit cooler out there, and we will hopefully see you in the coming months. So thank you again for coming.